Hello. Isn't that beautiful? What you're looking at is our project, a self-stabilizing system. I am Richard, and in this video I'll explain to you what we did in our project. Our project goal was to create a self-stabilizing pendulum. In this project we performed several tasks, like modeling, designing, building, programming, and testing. In this video I will go over these design stages and explain why they were necessary to create our final product. Our project is about stabilizing an inverted pendulum around a single point of rotation. A practical example of such a construction is a bicycle. If a bicycle is not moving, it will fall over on its side. Because gravity pulls on the bike, it will result in a system that will rotate, either clockwise or anti-clockwise, towards the ground. To prevent, to prevent such a tragedy, our project revolves around counteracting the rotation to keep it straight up. There are multiple approaches to do so, but our project revolves around using a flywheel to prevent it from falling down. The concept of a flywheel is quite tricky, but you can see it at work in this example. When the wheel gets accelerated in the clockwise direction, the arm gets pushed over into the anti-clockwise direction. The idea of our project is to use this behavior to keep the arm straight up. At first, we made a model of our problem. A model consists of the mathematical equations that explain the behavior of the components. It is a very complex piece of mathematics, so I won't go into too much detail. The model gives us insight into the problem at hand and helps us a lot with the design and programming phase of the project. The whole system is controlled by an Arduino control board. An Arduino is a mini computer that we use to run code to control our system. The Arduino takes the angle of the arm as input. The program will calculate how the wheel has to accelerate to keep it straight up. The Arduino then sends a signal to the motor to rotate at this acceleration. For our design phase, we made a 3D model in a 3D modeling program called Autodesk Fusion. This program gives us a good overview of the design and makes it possible to adjust many features during the design process. It also makes it very easy to convert the designed items to the real world using the laser cutter and 3D printer. Our first design consisted of a circular metal shaft that was mounted through two hinges. This shaft would act as the rotating axis of the system. The gyroscope is mounted onto the shaft. A gyroscope is a measuring device that can measure the acceleration around the point of rotation. We use these measurements to calculate the angle of the system. The shaft is connected to the arm. The motor is mounted through the arm to the flywheel. This construction will generate the angular acceleration to create the torque to stabilize the arm. In other words, this construction will power the arm to stabilize. After testing our original design, we discovered some flaws. We discovered that the motor wasn't powerful enough for our original design. We changed the dimensions and materials of the arm and flywheel numerous times to end up with a design that eventually worked. We also adjusted our control strategy. The method of using a gyroscope to measure the angle turned out to be very redundant. In the process of calculating the angle, it would result in a so-called drift. This drifting behavior would make it so the system forgets its stable position. This would result in a system that would collapse after a certain amount of time. After a lot of testing, we landed on our final design. For our final design, we swapped out the gyroscope for a rotary encoder. A rotary encoder is a measuring device that measures velocity instead of acceleration. Using this device, we can prevent the drifting problem we had in our original design. The rotary encoder is directly connected to the flywheel construction. The concept of the flywheel is the same as the original, but we changed the size of the components to make it work. Here you can see the final design of the project. In the end, we managed to make a self-stabilizing pendulum using a flywheel. Although it works, it does have a massive flaw. After a certain amount of time, the angular velocity of the wheel rotates so fast that we have to shut it down. This has to do with the fact that the set point of the system isn't completely in the middle. You can see this because the arm is slightly tilted to the right. This problem lies somewhere in the code, but we couldn't resolve it in the time we had. We can solve this problem by pushing the arm into the other direction. This, of course, goes against the principle of a self-stabilizing system, but it does look quite satisfying.